Hi, thanks for joining me today. I'm going to be going over problem 3 from week 3 of the Invariants Summer Puzzle Competition. As always, I'll leave a link in the description below to the Facebook page of the Invariants where you can find more details about the competition. This is the problem we have for today, and it involves directed graphs. So we have a directed graph G, which has n vertices, and it has the property that no four vertices, A1, A2, B1, and B2, have the directed edge from AI to BJ in the set of edges for every single pair ij within 1, 2. So in other words, all that means is that G does not have any subgraph of this form. So you take two vertices, and we'll call them A1, A2, and two other vertices, B1, B2, and you don't have all four of these directed edges. So this thing here would not be allowed as a subgraph of G. So the question is, we're going to define f of n to be the maximum number of edges in G. And then we want to prove that for some real number alpha, there exist two positive numbers, little c and big C, bigger than 0, such that Cn to the alpha is less than or equal to f of n, is less than or equal to big Cn to the alpha. And we also want to find alpha. So in other words, for directed graphs with this property here, we want to find bounds on the maximum number of edges in these graphs. And we want to firstly prove that it's kind of asymptotically polynomial. It grows at rate roughly n to the alpha, and we want to find what alpha is. Okay, if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into a solution. Okay, so I claim that alpha equals 3 over 2, and we're first going to prove the lower bound, i.e. that f of n is bigger than or equal to some constant little c times n to the 3 over 2. So the first thing I'm going to do is consider a prime p, so p is a prime. And what we're going to do is consider a directed graph G, and it's going to have p squared vertices. And now how are we defining these vertices? Well, let's say V is a vertex in our graph. Then it's going to have a corresponding point, alpha, beta, and it's going to have a corresponding line, L, which is of the form y equals ax plus b. And now, before I continue, I should probably say that this whole kind of argument, we're working in ZP. So everything, addition, multiplication, etc., is going to be in ZP. So this point here is a point in ZP, or in ZP squared, I should say. So alpha is in ZP and beta is in ZP. And this line here is also going to be in ZP squared, a line in ZP squared. Alpha is going to be some fixed number in ZP, and so is beta. Is B, sorry. Now, there are p squared vertices in our graph, and there are p squared choices for the point, and of course there are p squared choices for the line. There are p squared choices for the point because there's p choices for alpha, p choices for beta, and there's also p squared choices for the line because there are p choices for A and p choices for B. And I'm also going to insist this point here lies on this line here. So this point here, alpha beta, lies on this line. And we're also going to have the property that if we take another vertex in our graph, V prime, the associated point in ZP squared, alpha prime, beta prime, is going to be different from this guy here. And similarly, the line L prime, which is going to be of the form y equals A prime x plus B prime, this guy here, this line is going to be different from this line. So firstly, is this even feasible? Is this possible? And now, firstly, if we ignore the lines and we just associate a point in ZP squared with each vertex, definitely doable because there are p squared vertices, and then p squared choices for alpha, beta. Cool. But now we're introducing this line, and we are insisting that this line here passes through this point. And now things may become a little bit like, well, is this possible? And the answer is still yes, but it's a little bit more difficult to check. And I'm going to leave it as a little exercise for yourself to check that it is indeed possible to give each of these p squared vertices an associated point and an associated unique point in ZP squared and an associated unique line in ZP squared, such that that line passes through that associated point, and that whenever you take two different vertices, the points are different and the lines are different. But I'll leave that as an exercise to check for yourself that is indeed possible. And if you've seen Hall's theorem before, to check this should hopefully be pretty straightforward. That's a little hint, but it's probably also easy to check that it's possible without the need for Hall's theorem. but if anyone has a way to do it without Hall's theorem, it'll be cool to see how that's done in the comments. But yeah, to stop this video being really, really long, I'll leave that as a little exercise for you. Cool. V and V prime, different distinct associated points and different distinct associated lines. Now, how are we defining the edges in our graph? So we're going to say that, if you take V and V prime here are distinct, so we'll say that V and V prime, this directed edge, is going to be in our edge set if and only if, well, the line L passes through the point alpha prime, beta prime. So in other words, we take two distinct vertices in our graph, V and V prime, and the directed edge from V to V prime. And I guess it's important that V and V prime are distinct because otherwise we'd have self loops, which is not allowed. So the directed edge from V to V prime is in our edge set if and only if the line associated with V, this L, passes through the point associated with V prime, so alpha prime, beta prime. So this is how we are defining this edge set. And we can ask ourselves, how big is the edge set? Well, so how big is E of G? Well, suppose we fix V for now. Then we ask ourselves, how many choices are there for V prime, such that V prime lies in our edge set? So we fix V, so that means we know what L is. So in particular, we fixed A and fixed B. And so we want to know how many V primes are there, such that V prime is in our edge set. Well, that's essentially asking how many points are there that lie on L. And how many points lie on L? What is exactly P? Because once we fix V, we know what L is, and that fixes what A is and fixes what B is. So now we can only vary, say, X, and we vary X, through ZP, so it's 0, 1, 2, 3, all the way to P minus 1. And for each of those values of X, the value of Y is determined. It's A times X plus B, again, mod P. So we only have P choices, P different points that lie on the line L, but one of those points is alpha beta. And because that would correspond to VV, i.e. V prime equaling V, we don't include that one. So there's exactly P minus 1 different points that lie on this line which aren't that guy there. Cool. So that's once we fix V, but then how many choices are there for V? Well, it's P squared, because there are P squared vertices in our graph. So the number of edges in our graph is P squared times P minus 1. Cool. So our edge set is size P squared times P minus 1. And now one thing I will write is that if we expand this out, this is just P cubed minus P squared. And I'm going to write that as half P cubed plus a P squared times a half P minus 1. And I might ask why I've written it like this. So firstly, this guy does indeed equal this guy, because if I expand this out, this is a half P cubed plus a half P cubed minus P squared, so P cubed minus P squared, which is what we have here. But now, because P is a prime number, we know P is at least 2. It's a very trivial lower bound. P is at least 2, so half P minus 1 is at least 0, and of course P squared is at least 0. So this term here is non-negative, so that 3 shouldn't be there, it should be there, P cubed. So this guy here is certainly at least a half P cubed. So the number of edges in our graph is at least a half P cubed. And now what we want to do is check that this graph here also has the property that it doesn't have any subgraph of the form that looks like this. Okay, now why does it not contain a subgraph of this form? And let's see why. So this vertex here, this vertex here, this vertex here, this vertex here, each of these vertices is going to have a corresponding point and a corresponding line which passes through that point. For these two vertices here, all I care about is the line, so let's call it L1 and L2. And for these 2 points here, I care about the point, the associated point. So we'll call it alpha 3, beta 3, and then alpha 4, beta 4, say. And now, if this was indeed a subgraph of our graph G, what would the issue be? Well, essentially, we'd have a line, or these two lines, L1 and L2, would intersect at least twice. They'd intersect at this point here, and they'd intersect at that point there. But, if we now work outside ZP squared and just think about two straight lines, they can either intersect 0 times, if they're parallel, or they can intersect once, which is the case most of the time, or they intersect infinitely many times, and that's if they're the exact same line. Now, it's a very similar thing in ZP, or ZP squared. These two lines aren't the same, by assumption, because they correspond to two different vertices, and we're insisting that the lines are never the same. So they can either intersect once or 0 times, but they certainly can't intersect 2 times, or 2 or more times. So this is a contradiction. This is impossible. So certainly this graph G satisfies our properties. And while it has p squared vertices, and it has at least a half p cubed edges, so certainly if n was p squared, so if it was the case that n was the square of a prime number, we found a directed graph G which has, v of G is bigger than or equal to a half p cubed, which is just a half n to the 3 over 2. So that would kind of prove it in the case where n is a square of a prime, because we've shown that it's bigger than or equal to a small constant times n to the 3 over 2. So obviously f of n therefore is going to be bigger than this, and f of n therefore is bigger than or equal to a half n to the 3 over 2. But of course this is only in the case where n is p squared, n is the square of a prime. What if n is not the square of the prime? But that's where we can just use a quite nice result from number theory to help us. So it's quite cool how we're integrating number theory and graph theory. But yeah, let me clean up the whiteboard and we'll quickly look at the case where n is not the square of a prime, and that's going to generalize this lower bound case, and then we can move on to the upper bound. Okay, so we've just proved that f of n is at least a half n to the 3 over 2 if n equals p squared. But now, as I say, what if n is not p squared? What if n is not the square of a prime? Well, we can use a very famous result from number theory, which is known as Bertrand's postulate, which says that there's always a prime number between x and 2x for kind of any positive real number x. So what we can do is, now we're going to fix n, and n doesn't necessarily have to be the square of the prime. And now what we're going to do is let p be a prime in the interval, just square root of n all the way up to in the interval a half square root of n all the way up to the square root of n. Okay, so this is of the form x to x, so there's certainly a prime in them. We'll just say that p is the biggest prime in that interval if there are many primes in that interval. So p is the biggest prime in that interval there. And now, well, we're just going to kind of follow on with the same argument. Well, we know that p is therefore less than or equal to root n, so certainly p squared is less than or equal to n. And of course, if p squared equals n, i.e. p equals root n, then we're kind of done. And if p squared is strictly less than n, what we're going to do is we're going to just do the case we had up here. So we're going to just, so if p squared is strictly less than n, because we know how to deal with the case where p squared equals n, if p squared is strictly less than n, well then we're just going to do up the case where we have p squared vertices. So I guess we could say n prime is defined to be equal to p squared. So we're going to do what we had before with the directed graph G, which had p squared vertices and all that sort of stuff. And we're then just going to add on n minus p squared. So whatever that is, just empty vertices. So this guy here will, we'll be able to get a directed graph with p squared vertices, which has at least a half p cubed edges, and it has the property that we need. And then we're just going to add on n minus p squared empty vertices. So this is just to make a new directed graph G, which still has it has n vertices, and it still has a property that no two vertices have two common neighbors, for example. So this is now a new graph, and how many edges does it have? Well, the number of edges is at least a half p cubed. So if we call this graph, say G prime, the number of edges in this graph is just the number of edges in this guy here, which we know is at least a half p cubed. But p, we know, is at least a half root n. So this is going to be at least a half times root n cubed, which is just n to the half cubed, or a half n to the half cubed. And a half cubed is an eighth. Multiply that by a half there is a 16th. And then we've got n to the 3 over 2, like so. So we get that the number of edges in this new graph, G prime, is at least a 16th times n to the 3 over 2, like so. And that is still fine for us. It's some small constant times n to the 3 over 2. And this holds for arbitrary n because of this nice, Bertrand's postulate, which tells us that there's always a prime between x and 2x. So this tells us f of n is bigger than or equal to c times n to the 3 over 2, for c equals a 16th. And now at the end of the video, I'll quickly mention how potentially you can think about making this C a bigger number, so kind of strengthening the bound. But for now, we've solved the lower bound case. Let's move on to the upper bound case, i.e. proving that f of n is less than or equal to some constant big C times n to the 3 over 2. Okay, so now we're going to prove that f of n grows at most, some constant times n to the 3 over 2. And now what we're going to do is take an arbitrary graph of this form. So take an arbitrary directed graph G, which has the property that no two nodes will have no two common neighbors, kind of thing. So what we want to do is then prove that f of n, the number of edges in that graph is at most some constant times n to the 3 over 2. Cool. The way we're going to do that is firstly take our graph, and then we're going to let, for each vertex, so if we have our graph G, and it has vertices v1, v2, all the way up to vn, we're just going to define di to be the out degree of vertex vi. So the number, so if this is our vertex vi, then the out degree is the number of edges going out of it. So the degree of vi here would just be, or di here in this case would be 2, for example, because there's 2 edges going out of it. Cool. So firstly, we can kind of do Euler's handshaking lemma and say that the number of edges in our graph is just going to be the sum of the degrees in our sum of the di's from I equals 1 to n. And now you might say, wait, why isn't there a 2 somewhere here? And well, that's because each edge in our graph is only contributing 1 to the degree, because each edge has it only has one direction associated with it. It can't be an edge with kind of arrows both ways. So certainly the number of edges is equal to the sum from I equals 1 to n of di. Now I'm going to make a lemma here, which we're going to prove. And that is that some quantity is less than or equal to another quantity. What are these quantities? So the sum from I equals 1 to n of di choose 2. I claim that this guy here is less than or equal to n choose 2. So this is just, each of these di's, we define the out degrees. We take the sum of them, choose 2. Or, we do di choose 2 for each of the i's, sum them up, and that's going to be less than or equal to n choose 2. Let's prove it. So the proof for this is we're going to find an injective map from a set which has this size to a set which has this size. So we're going to set S to be the set of, we'll say, Vi, Vj, Vk in our vertex set, for which Vj is distinct from Vk. And we have Vi, Vj, Vi, Vk, both in our edge set. Okay, so this is how we're defining S. It's the triples Vi, Vj, Vk, where the last 2 elements are distinct. And we have an edge from Vi to Vj and an edge from Vi to Vk. Well, what's the size of this set here? Well, once we fix Vi, so for each I, we have a fixed Vi. And then what are the choices for Vj, Vk? Well, it's simply going to be di choose 2, because we need the fixed Vi. We'll have Vj here, Vk here. Perhaps it's also connected to some other edge, like this. What are the number of ways of choosing Vj and Vk as its out degrees? Well, it's 3 choose 2 in this case, so it's the di choose 2. The number of ways we can choose Vj, Vk as kind of neighbors of Vi is, well, it's the total number of neighbors choose 2. So that's so this guy here has size sum from I equals 1 to n of di choose 2, because once you fix I, you then have di choose 2, then of course I could be anything from 1 to n. So the size of S here has this left-hand side size, and then we're just going to define the set T to be equal to this set of Uj, Uk in our vertex set, for which Uj does not equal Uk. So essentially, the number of pairs of vertices where both those pairs aren't the same. Number of ways of doing that is n choose 2. The number of ways you can choose 2 different vertices from this guy here. And what we want to do is find an injective map from this set here to this set here. And the way we're going to do that is simply by setting, our injective map we're going to call f from S to T. And it's going to have the property that f of Vi, Vj, Vk, this guy here, is just going to map to Vj, Vk. And of course this guy is in T, because Vj, Vk are distinct, So this guy here is going to be in T. And now we just need to check that this guy here is injective, and that follows from the fact that we have this property here, that this guy here is forbidden. Because if we had, two distinct elements in S mapping to the same guy, well, then that would correspond to, say, VI here, VJ, VK, and then VI prime. We'd have this kind of setup, like so. So if you had two different points, say VI, VJ, VK, and VI prime, VJ, VK, both mapping to the same point, then it would, we'd have something like this, which is forbidden. So that tells us that this is an injective map. So certainly we get this inequality here. So that is our proof done. So that proves that this lemma here holds. But now what we want to do is just a little bit of algebra on this DI stuff using EG, or I should say the number of edges in our graph. Using a bit of Cauchy-Schwarz, we should hopefully be able to find a bound on E of G. But let me clean up the whiteboard and we'll just do that. Okay, so we have the number of edges in our graph is just the sum of the DIs, and the sum of DI choose 2 is less than or equal to n choose 2. We're going to start with this inequality here and just expand it. So we get the sum of DI squared minus DI all over 2 from I equals 1 to n is less than or equal to n squared minus n over 2. Next obvious thing, just multiply both sides by 2 to get rid of that. And then what we're going to do is just add on the sum from I equals 1 to n of DI on both sides. So we get the sum from I equals 1 to n of DI squared is less than or equal to n squared minus n plus the sum from I equals 1 to n of DI, but that is just the number of edges in our graph. Cool. So that's what we have. Now what we want to do is have a play with this guy here. We're going to use Cauchy-Schwarz and the Cauchy-Schwarz inequality on this guy here. So if we just consider, the sum from I equals 1 to n of DI, well, this is just exactly d1 times, if you think of the vector with the dot product, so d1, the dot product of this vector and this vector is just going to be d1 times 1 plus d2 times 1 plus d3 times 1, and so on, and that's just the sum from I equals 1 to n of di. But by the Cauchy-Schwarz inequality, this is going to be less than or equal to the magnitude of this times the magnitude of that. The magnitude of this guy here is just the square root of d1 squared plus dot 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 plus dn squared, and multiplied by the magnitude of this guy here, which is just going to be the square root of n, because it's 1 squared plus the square root of 1 squared plus 1 squared plus 1 squared plus so on n times, which is of course the square root of n. So we get the sum from I equals 1 to n of di is less than or equal to this guy here. We can square both sides and notice that this guy here is just e, so perhaps I'll just bring it up here. So we're going to get e squared, where e is just shorthand for the number of edges in our graph. E squared is less than or equal to n times the sum of di squared from I equals 1 to n. So that's what we have. So we can have that, if we rearrange this, we get that this guy here, the sum from I equals 1 to n of di squared is bigger than or equal to e squared over n. So now what we can do is just rearrange this inequality here. So if we get rid of this middleman, we've got e squared over n is less than or equal to n squared minus n plus e of g. So if I just make some space down here, let's multiply through by n and then bring this onto this side. So we're going to get e of g squared minus n e of g is less than or equal to n cubed minus n squared. This guy here, we can now just complete the square and get e of g, or I should say the number of edges in our graph, e of g minus n over 2 squared minus n squared over 4 is less than or equal to n cubed minus n squared. Let's just clean up. E of g minus n over 2 squared, bring this onto that side and then square root. We're going to get that e minus n over 2 is less than or equal to the square root of n cubed minus 3n squared over 4, like so, and then add on n over 2 to both sides. So we get e is less than or equal to n over 2 plus the square root of n cubed minus 3n squared over 4. And now this does look like a bit of a horrible expression, but this thing here, n cubed minus 3n squared over 4, is certainly going to be less than n cubed. So I guess we could, if we wanted to, just get rid of this guy completely, like so. And now we've got n over 2 plus n to the 3 over 2. I get rid of this, like so. And of course, we can probably say that this is certainly going to be less than or equal to c times n to the 3/2 for large enough c. So you can just go ahead and work out what c is there. It's probably, c equals 10 looks more than sufficient, but I'd probably just go ahead and check that. But certainly the number of edges grows at most grows at most times a constant times n to the 3/2. And that finally solves our problem. I hope that has all made sense. I apologize for my pen running out at the end there, so I hope you managed to follow along. But essentially, here to here was just a bit of algebra using the Cauchy-Schwarz inequality as well. But that solves our problem. This video is getting too long already. Thank you for watching. Do check out some of my other solution videos as well if you haven't already, and do check out some of the other videos on my channel as well. If you are new to the channel, please do consider subscribing, but I'm going to stop waffling now. Thank you for watching. I'll catch you in the next one. Have a great day.